sometimes if we've got a function, it is easier to differentiate it if we can write the function as a polynomial, and then it becomes easy to differentiate and integrate and to do some other things. So therefore we can approximate e to the x to some sort of polynomial, a plus bx plus cx squared plus cx cubed plus ex to the fourth plus fx to the 5, etc. And if we can find the values a, b, c, d, e, and f, we can see it's it will such that it will approximate to e to the x. Now, in order to be able to do this, the original function needs to be able to differentiate it and find its value at 0. And this is known as Maclaurin's expansion. Okay, and I'm just going to show you graphically to begin with, and then in later videos we'll actually prove this result. Okay, so if we look at the function, here is the function f of x is equal to e to the x. And by the way, this GeoGebra app I will put in the link in the notes of the video. Okay, if we take where x is equal to 0, i.e. where it cuts the y-axis here, and if I click it, okay, if I put x is equal to 0 into the function, I'll get e to 0, and that will be equal to 1. So that would be like my value of a in my polynomial expansion that I'm going to come up with. Now, if I change n, the next one to be 2, okay, it becomes a slightly better approximation near the x is equal to 0. Okay, and therefore the next term will be f of 0, which I've already worked out, plus f dash of 0, which is e to the 0. The good thing about differentiating e to the x, you always get itself. So e to 0, which is 1, and then e to the 0 times x, which is 1x. But I could probably make the approximation even better if I take n is equal to 2. You can see it looks a little bit better now. And in this case, it will be f of 0 plus f dash of 0, which is e to the 0 plus e to the 0. The next one will be the second derivative divided by 2 factorial. And we'll see why it's divided by 2 factorial in the later video. X squared will give me a better approximation. So that gives me e to the 0 plus e to the 0 x plus e to the 0 over 2 x squared, which is 1 plus x plus a half x squared. Okay, and I can continue the process. So when 3, you can see it is looking even better now. It's much better, look much closer. And then if the extra term that I add in will be the third derivative at 0 divided by 3 factorial x cubed, which is 1/6 x cubed x. So the red curve represents this. Okay, and then let's try 4. It looks even better there. Okay, so that's going to be 1 plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the 4th. Okay, so you just keep differentiating e to the x. It's great because it doesn't matter how many times you differentiate e to the x, it's e to the x. Okay, so the next term will be f to the 4th derivative at 0 divided by 4 factorial. And obviously if we do when n is 5, again, looking even better, okay, we get the extra term of the 5th derivative at 0 divided by 5 factorial over x to the 5. It's e to 0, 5 factorial is 120 x to the 5. Okay, and this procedure will continue. This is known as Maclaurin's expansion. The formula for it is here at the bottom here. You can look at this GeoGebra app for yourself by clicking in the notes. Now we can just do n is equal to 6, because it's even getting better, particularly down at this end. N is 7, n is 8, n is 9, n is 10, and it's sort of getting better and better. Well, so n is 10, it's that one. And we can see it's very, very good here. We see it becomes a reasonably good approximation to the original function. So we can write e to the x as a polynomial and then work out the values of a, b, c, d, e and f by keep differentiating each time, and you'll see this in a proof that I will show you in a minute. Okay, I hope you've understood, and the result is called Maclaurin's expansion. I hope you've understood, and I thank you very much for watching.